My dear students, today we are going to discuss about the physiology of hearing. I am Dr. T.B. Ram Singh, Assistant Professor in the Department, Janims Porompat. Before we come to the physiology of the hearing, we need to know what is sound. Sound is the vibration or oscillation which travels in solid, liquid, or air medium. Now, hearing on the other hand is the perception of the sound, and the listening will come across the listening. Listening is important because you may not be listening even though you are hearing. So when we say listening, it means that you're paying thoughtful attention and consideration to the sound that you heard. Sound velocity, it is around 344 meter per second in air medium. Sound travels faster in the solid medium than that of the liquid and the air medium. This portion, I think it has been discussed. You all know about this. But what we have to know is that the sound frequency that we can hear, that a human can hear, is 20 hertz to 20,000 hertz. As you all know, sound has got a frequency and then amplitude. So this amplitude will denote the intensity of the sound, and this is being expressed as a decibel. Then you will come across the word impedance, and you have to know that impedance is nothing but it is the resistance which is offered by a medium to the sound. Now for hearing, we require a stimulus, and that is your sound. So when a sound is presented, it travels through the ear medium, then it hits the tympanic membrane, causes the vibration of the tympanic membrane, then this vibration is transmitted through the ossicles to the footplate of the stapes, and it causes a vibration of your endolymph, and this transmits it to the basilar membrane. So this is your conduction of the sound. This is in the form of the mechanical energy. And what is happening is the sound, when it travels from the air medium to the liquid medium, 99.9% is reflected normally, but the nature has devised the middle ear in such a way to match this impedance of the liquid. As you know, the inner ear contains the liquid, and the middle ear and the external ear has got the ear medium. So we have the impedance matching mechanism to counter this loss of the 99.9% of the sound when it passes from air medium to the liquid medium. So this is the conduction of the sound. We'll be discussing more in detail about the impedance matching mechanism in the later slides. Then you have the transduction of the sound. Transduction of the sound is we are going to say up to the middle ear, it is the mechanical energy. Now this mechanical energy is going to be converted into electrical energy inside the inner ear. So this is the transduction of the sound. So how it happens is, say when the basilar membrane vibrates, then there is a shearing force which is created between your hair cells and tectorial membrane, and there is a this creation of the shearing force will lead to the influx of potassium ions inside the hair cells. When the potassium ions enters inside the hair cells, there is a series of chain reactions leading to the influx of the calcium ions. And when the calcium ions enters inside the hair cells, they causes the release of the neurotransmitters from the synaptic vesicles, and it causes the action potential in the neurons. The bipolar cells has got the dendrites which innervates the hair cells, and the axons of these bipolar cells, they are the one which forms your cochlear nerve, and from the cochlear nerve it will traverse to the dorsal and ventral cochlear nuclei, and from there it will cross and uncross fibers will traverse through the superior olivary complex. Then you will have, it will passes through the inferior colliculus, medial geniculate nucleus of the thalamus, and ultimately to the auditory cortex, which is the area 41 of the Brodmann classification. So that is your neural transmission of the sound and central auditory processing. Now the importance of the hearing is it will help in the localization of the sound, and this is very important. It is a kind of warning system. Suppose you are traveling in a busy street, and if there is a honking of the vehicle, it warns you from where the vehicle is coming and you will be protected. So the localization of the sound is very important for the survival. Next is for the communication. If you want to talk with a friend, if you want to know the behavior of a person, if you want to communicate, this is, you require the hearing. So the personality of a person can be known from the way he talks. So this is very important. It is a very complicated, the hearing is very important. Then conduction of the sound. 99.9% of the sound is reflected while traveling from the ear to the liquid medium. This is because the impedance of the liquid is more than that of the ear. So to counter this loss of the sound, we have the impedance matching mechanism of the external auditory canal, then tympanic membrane and the ossicles. So you have the sound which is, say the vibration of the sound will produce the vibration of the tympanic membrane. Then ultimately this is going to be transmitted through the handle of the malleus and incus, then to the stapes, and ultimately to the oval window. But you have to know that the size of the tympanic membrane is around 89 to 90 millimeters square, and the amount of the sound energy received by the tympanic membrane, it converges to the small area that is your 3.2 millimeter in the oval window. So this this increases the sound transmission. This converts the sound which is low pressure and a high displacement into high pressure and the low displacement in the oval window. So you have the low pressure and high displacement type of the sound in the tympanic membrane, and high pressure and the low displacement in the oval window. So this type of the low pressure and the high pressure and the low displacement sound is suitable for the cochlea. Again, if you compare the handle of the malleus, the length of the handle of the malleus and that of the short process of the incus, it is around 1.3:1, and this also gives you a lever action, and this also magnifies the sound. So if you compare the diameter of the tympanic membrane to the diameter of the oval window, it is known as the area ratio. It comes to around 21:1, and the ossicular lever action is 1.3:1. So this gives the magnification of the sound. But to some authors, they believe that the whole area of the tympanic membrane do not vibrate effectively. So the effective vibratory area is around 45 millimeters square, and if you take the ratio of the effective vibratory area to that of the diameter of oval window, it comes to around 14:1. So that is going to be discussed in the later slides. So before coming to that main transformer action or the impedance matching mechanism, I want to tell you the functions of the when to go from outside to inside. So this is the functions of the external ear. Now the pinna, starting from the pinna collects sound from a wider area. So from the pinna the sound will be collected, then this will be transmitted through your external auditory canal, in the external auditory canal, this tube, the size of the tube, this is very important because it will help in, you know, cut out the unwanted frequencies. So it will, they have got a resonant frequency. So this is 3000 hertz for the external ear canal. So when the sound travels through the ear, the external ear, what it does is the pressure of the sound will be more near the tympanic end than that of the outer part. So it will help in the vibration or effective vibration of the tympanic membrane. The concha, the resonant frequency is 5000 kilohertz. The external auditory canal, the resonant frequency is around 3000 kilohertz. So this frequency, this particular frequency of the sounds are being, you know, transmitted better in the by the external canal. So it will cut out the other unwanted frequencies. And the important function of the pinna is it will help in the localization of the sound. So it will block the sound which is coming from the other side. So that will say by the, we call it the head curve shadow. So that will help in the localization of the sound. So there is a resonant frequency. This is a particular frequency which travels, you know, which say external auditory canal. It will have a resonant frequency of around 3000 hertz. So the other frequencies will be cut out. The tympanic membranes will have a resonant frequency of 800 to 1600 hertz. Middle ear will have 800 hertz. Occipital chain will have 500 to 2000 hertz. So ultimately you can see the conversational voice, the, you know, the voice that we are interested are all within 500 to 3000 hertz. So our say our voice or human voice usually, you know, it ranges from 500 to 3000 hertz. So a baby or a female voice, they will be a little bit on the higher spectrum, that is 1000 2000, whereas a male voice, they will be a little bit on the lower spectrum, say 500 to 1000, like that. Now coming to the role of the tympanic membrane, we have got a particular characteristic of the tympanic membrane that is known as the curved membrane effect. Now this will also help in the magnification of the sound. As I told you before, the external ear canal, the particular, you know, the shape of the external ear canal, what it does is it will increase the sound pressure near the tympanic end. Now this pressure will be transmitted to the tympanic membrane. We have got a particular characteristic that is known as the, you know, tympanic membrane buckling effect. Now what it does is the tympanic membrane is fixed at the annulus and also to the handle of the malleus. Now when the sound strikes the tympanic membrane, this part of the tympanic membrane, or the part which is away from the handle of the malleus and the annulus, there is a more displacement. There is more displacement, but the pressure will be low. Whereas at the part of the malleus, so in the malleus, since it is fixed there, the displacement will be less, but the pressure will be more. So this is how it converts the high displacement, low pressure to low displacement and the high pressure sound. So this is again going to be transmitted through the incus, then to the stapes and to the oval window. So this is known as the curved membrane effect. And this type of the sound, that is your low pressure high displacement sound to the high displacement to the high pressure low displacement sound, is more suitable for the cochlea. So this is very important for you, and it is often asked in the exam also. So role of the middle ear, or the transformer mechanism, or the impedance matching mechanism. This I have told you before also. You have to know that the handle of the malleus is to long process of the incus is around 1.3:1. This is also known as the lever action. Now you have the hydraulic action of tempering membrane. Even though the size of tempering membrane is 89 millimeter square, we take the effective vibratory area of tempering membrane, that is 45 millimeter square, and then you compare it with the size of the full plate of step-piece, that is 3.2. So if you take a areal ratio, it will come to around 14:1. Now this 14:1 you multiply with the 1.3, it will come to around 18.2. So that is the gain of the, you know, say your sound. So you will have this transformer ratio is also known as transformer ratio. So this total transformer ratio, it comes to around 18.2. Now this is not the only magnification that we can get. I told you before, the external auditory canal also will increase the sound magnification. On top of that, we have got another mechanism known as the phase difference. Now what is this phase difference? See, I told you before, the sound has got a crest and a trough, or a rarefaction and a compression. So the compression is the part which we take as a crest if you convert into a waveform. The rarefaction is the part which is taken as a trough, the depression part. So what happens is when the compression hits the oval window, then in the round window, the uh, the rarefaction will hit the round window. So when the rarefaction hits the oval window, the compression will hit the round window. So this is the phase difference. So this phase difference is being created by the intake tempering membrane. Means the sound will not travel, will not hit exactly. If there is a total perforation, then this phase difference will be gone. But if there is a tempering membrane, the sound will be going through the ossicles, from the tempering membrane to the ossicles, then to the oval window. So when the compression hits, that part of the sound will not be hitting your round window. So the round window will be in the phase of the rarefaction. So this phase difference is created by the intake tempering membrane, and this will give you a gain of around 4 decibel. Okay. This slide I have included to tell you a little bit about the role of the middle ear muscles. In fact, this is part of the contents of the middle ear. That question was asked this time. I'll be coming to detail contents of the middle ear cavity, but pertaining to the physiology of the hearing, you have to know a little bit about the functions of the tensor tympani and stapedius muscle. So these muscles are very important because they act as a dampener. Dampener means when you are exposed to loud sounds, your inner ear has to be protected, and that is being done by the help of the tensor tympani muscles and stapedius muscle. Now how it happens, we'll discuss. So first is we'll discuss about the stapedius muscle. So stapedius muscle is present in the posterior part. In the posterior part, it is coming out from the pyramid, then it is attached to the neck of the stapes. Now whenever you are exposed to the loud sound, then what happens is it will pull the stapes, backwards and also outwards. So the foot plate will be pulled outwards and backwards. Now whenever there is a loud sound, then the movement, the piston like movement of the oval window will be affected, because it will be converted into a sliding movement. So the inner ear is protected. Again, similarly, another action is your tensor tympani muscle. So tensor tympani muscle will be coming out from the semicanal for the tensor tympani, that is present just above your suction tube opening in the anterior part. Then it will be coming out, and this will be attached to the handle of the malleus. Now the handle of the malleus. So whenever there is a loud sound, then what happens? This muscle will contract, and when this muscle contracts, the handle of the malleus will be pulled inside, that is medially. So this will make the tempering membrane tense, and the effective vibration will be reduced. So this is how it is going to protect the inner ear. So next we will discuss the role of the inner ear. So here we have mentioned before also, when we convert mechanical energy to the electrical energy, that is conversion of the one energy to another form of the energy, this is known as a transduction. So in the inner ear, what we're going to do is we're going to convert the mechanical energy to the electrical energy. Okay, Now, the first thing that is required is the movement of the footplate of the stapes by the sound. Now, this movement of the footplate of stapes will transmit the vibration to the basilar membrane, and this basilar membrane vibration will produce a shearing force between the tectorial membrane and your inner hair cells. And what happens is, when this shearing force is created, the potassium ion channels will open up. Then potassium ions from the endolymph will enter inside the inner hair cells, thereby creating a cochlear microphonics, that is a change in the action, change in the say potentials. So this is going to trigger a nerve impulse. Now, how it triggers the nerve impulse? See, potassium entering inside the inner hair cells. This will cause the influx of the calcium channels inside the inner hair cells. And when the calcium channels influx occurs, then the synaptic vesicles which are already inside the inner hair cells, they will release the neurotransmitters, and this neurotransmitter will go and then cause a action potential in the dendrites of the bipolar cells. Okay, that is how an action potential is being created. Now this, from the dendrites of the your bipolar cells, it will travel through the axons of the bipolar cells. So axons of the bipolar cells will be forming your cochlear nerve. So from the cochlear nerve, it will go to the different neural pathways, ultimately will reach the auditory cortex. Okay, now you have to know about the traveling wave theory of von Vecchi. He got von Vecchi, he got Nobel Prize in 1961 because of this theory, because of his work in the inner ear. And what he mentioned is that a particular frequency of the sound will cause displacement of the, or the maximum amplitude of displacement of basilar membrane at a particular area. So that frequency, that particular frequency will have a particular maximum amplitude of displacement. So that frequency will be represented in that area. Okay, so this idea gave rise to the another theory, that is your tonotopical localization of the sound, which means that the low frequency sounds are arranged at the apex, and the high frequency sounds are being registered at the basal turn. Okay, so this is known as the tonotopical localization of the sound. Now this tonotopical localization is also maintained at the auditory cortex also. In the auditory cortex, it has got a columnar organization. Okay, so in the Brodmann or the primary auditory cortex, also known as the your Brodmann area 41. So there the arrangement is a columnar organization. Okay, the neural pathways, I have discussed this in the previous class also, in the anatomy also anyway. So the hair cells, they are innervated by the bipolar cells. So these bipolar cells are present in the spiral ganglion of the cochlea. Now the central axons of the bipolar cells, they will form the cochlear nerve, and they will synapse at the dorsal and ventral cochlear nuclei. So from there, cross and uncross fibers will go through the superior olivary complex. From there, lateral lemniscus, then the inferior colliculus, and your medial geniculate nucleus, then to the auditory cortex or the area 41. I think we have discussed this before also. Now coming to certain electrical potentials, so first thing is that you have to know what is endocochlear potential. So endocochlear potential is always present. Endocochlear potential is the inside the endolymph, inside the scalea media, there is maintenance of always a positive IT millivolt, and that is because of the potassium ions secreted by the sodium potassium ATPase in the stria vascularis. So this produces a potential. This is known as the endocochlear potential. It's just like a battery which drives the uh, say all the other potentials. Now Next is your cochlear microphonics. So this is we have told you before. So movement of the basilar membrane in response to sound. So it produces the or reduces the resistance of the tips of the hair cells. Then there is a inflow of the potassium ions into the hair cells. So this produces a voltage fluctuation, that is your cochlear microphonics. So it is a kind of the alternating current, unlike the intercochlear potential, which is a direct current, and this is mainly generated from the outer hair cells. Okay, so this is you have to know, see, the cochlear microphonics are mainly generated by the outer hair cells. Then you have the summation potentials. So these summation potentials are being generated by the inner hair cells. Okay, now the action potential is generated at the level of the nerves. So the spiral ganglion will be here. So this is the dendrites of the your say bipolar cells. So cochlear microphonics by the outer hair cells, summation potentials by the inner hair cells, and the action potential by the your bipolar cells or the cochlear nerve. Now this last slide I have kept because this time this question was asked, what are the contents of the middle ear? Now when we say this is not related with the physiology of the hearing, but I wanted to teach you because this sometimes checks your common sense also. See, when you say contents of the middle ear, the most important contents of the middle ear is ear. So I think most of you missed it, ear. Now then you have the three ossicles, that is your malleus, incus and stapes. Then you have the two muscles, stapedius muscle, tensor tympani muscle. This has been discussed also. Then you have mainly two nerves. One is the chorda tympani. You have got facial nerve also, but that is embedded inside, so I have not included it. You have the chorda tympani, and then you have the tympanic plexus. Then vessels, you have got superior tympanic artery, then you have the anterior tympanic artery, then you have the branches or corticotympanic branches. So these vessels all are mentioned here. So you have to know about these vessels also. Then you have the mucosal folds and ligaments. If you do not know, if you've forgotten, then you may not write this, but you can just write at least a mucosal folds and ligaments. But if you want to get better marks, then you have to mention this is the malleus, this is the malleus, this is the incus. So you have got the say this is a superior malleolar fold. Then you have the anterior malleal ligament folds, then anterior malleolar ligament, then you have the lateral malleolar folds, then you have the lateral inguinal fold, then you have the superior inguinal fold, then you have the posterior inguinal fold, then you have the this is actually the stapedial fold, then you have the tensor tympani fold. So these are the different folds that you can mention. If you have forgotten, you can at least mention mucosal folds and ligaments. Okay, so this was asked this time in the as a short note in the final exam. So that is about the physiology of the hearing. So read hard. I hope you will do good in the coming exam. So all the best for the exam. Thank you.